Welcome to Chapter 2 of Class 9 Science. Is matter around us pure? In this fascinating chapter, we'll explore what makes a substance pure and learn to distinguish between different types of mixtures. When we see pure written on milk packets or salt containers, it means something different to scientists than to common people. For scientists, a pure substance consists of only one type of particle with identical chemical nature. Most of the matter around us, from the air we breathe to the soil beneath our feet, exists as mixtures of different pure substances. Get ready to become a purity detective and learn to identify different types of mixtures. Let's begin by understanding what mixtures are. A mixture contains more than one pure substance mixed together in any proportion. The key characteristic of mixtures is that their components retain their individual properties and can be separated by physical methods. In Activity 2.1, when different groups mix copper sulfate with water, we observe two types of mixtures. Groups A and B get homogeneous mixtures where the composition is uniform throughout. These are called solutions. Groups C and D get heterogeneous mixtures with physically distinct parts and non-uniform composition. This simple activity shows us that mixtures can be either homogeneous, where everything looks the same throughout, or heterogeneous, where we can see different components. Now let's explore different types of mixtures in detail through Activity 2.2. When we test different samples, copper sulfate crystals, chalk powder, and milk, we get three different types of mixtures: solutions, suspensions, and colloids. Solutions are homogeneous mixtures with very small particles that don't scatter light. Suspensions are heterogeneous mixtures with large particles that settle down and can be filtered. Colloids appear homogeneous but are actually heterogeneous with medium-sized particles that scatter light. This light scattering is called the Tyndall effect. Understanding these differences helps us explain why milk appears white and cloudy while salt solution appears clear. Let's dive deeper into solutions and their concentration. In Activity 2.3, we discover that different substances have different solubilities, the maximum amount that can dissolve in a given amount of solvent at a specific temperature. A solution that contains the maximum amount of solute is called saturated, while one that can dissolve more solute is unsaturated. We can express concentration in different ways: mass by mass percentage, mass by volume percentage, or volume by volume percentage. For example, if we have 40 grams of salt dissolved in 320 grams of water, the mass percentage is 11.1%. Different substances like potassium nitrate, sodium chloride, and ammonium chloride show different solubility patterns with temperature changes. Now let's compare suspensions and colloids. Suspensions are heterogeneous mixtures where solid particles don't dissolve but remain suspended. The particles are large enough to be visible, scatter light, settle when undisturbed, and can be filtered. Think of muddy water. You can see the particles, they settle down, and you can filter them. Colloids, on the other hand, are special heterogeneous mixtures that appear homogeneous. Their particles are smaller than suspensions but larger than solutions. They show strong Tyndall effect, don't settle, and can't be filtered normally. Milk, blood, ink, and fog are all colloids. The Tyndall effect is why we can see sunlight beams in forests or projector beams in dusty rooms. Colloids are everywhere in our daily life, and they're classified based on the states of their two components: the dispersed phase, the particles, and the dispersion medium, the surrounding material. We have aerosols like fog and smoke, emulsions like milk and face cream, foams like shaving cream, sols like milk of magnesia, gels like jelly and cheese, and solid sols like colored gemstones. Each type has specific characteristics and applications. To separate colloids, we need special techniques like centrifugation, which uses high-speed spinning to separate particles based on density. This is how we separate cream from milk or different components from blood. Now let's understand the difference between physical and chemical changes. Physical changes involve no new substance formation. The composition remains the same, and the changes are usually reversible. Melting ice, boiling water, dissolving salt, and cutting paper are all physical changes. Chemical changes, on the other hand, involve the formation of new substances with different properties. These changes are usually irreversible. Burning paper, rusting iron, cooking food, and digestion are chemical changes. A burning candle shows both changes. The wax melting is physical, while the wax burning is chemical. Understanding these differences helps us predict how materials will behave under different conditions. Let's explore pure substances, which are classified as elements or compounds. Elements are the basic forms of matter that cannot be broken down into simpler substances by chemical reactions. Robert Boyle first used the term in 1661, and Lavoisier established the experimental definition. Elements are classified as metals, shiny, conductive, malleable, non-metals, varied colors, poor conductors, and metalloids, intermediate properties. There are over 100 elements known, with 92 occurring naturally. Most are solids, 11 are gases, and only 2 are liquids at room temperature, mercury and bromine. Compounds are substances composed of 2 or more elements chemically combined in fixed proportions, with properties completely different from their constituent elements. Now let's examine the crucial difference between mixtures and compounds through Activity 2.4. When we mix iron filings and sulfur powder, we get a mixture where both components retain their properties. The iron is still magnetic, and sulfur still dissolves in carbon disulfide. But when we heat this mixture strongly, a chemical reaction occurs, forming iron sulfide, which has completely different properties. It's not magnetic, and sulfur doesn't separate in carbon disulfide. This demonstrates that mixtures are physical combinations where components retain their properties, while compounds are chemical combinations with new properties. This fundamental difference explains why we can separate mixtures by physical methods but need chemical methods to break down compounds. Finally, let's review everything we've learned. Pure substances can be elements or compounds, while mixtures can be homogeneous or heterogeneous. Homogeneous mixtures include solutions, while heterogeneous mixtures include suspensions and colloids. Each type has distinct properties related to particle size, light scattering, stability, and filterability. Physical changes don't create new substances, while chemical changes do. Understanding these concepts helps us make sense of the world around us. Why milk appears different from salt water, why muddy water settles, and why iron rusts but doesn't separate back into iron and oxygen easily. This knowledge forms the foundation for understanding more complex chemical concepts in higher classes.